In our third example, we have 3 objects, which makes the problem a little bit more time-consuming and a little bit more tedious. However, the actual method itself is not anything too complicated. In this problem, we are going to try and find the total net force acting on A, acting on B, and acting on C. So what total force is acting on these, because now we have multiple masses that are each individually exerting forces on the other masses. So the general problem-solving process we're going to use is going to be draw our forces, calculate those forces using the universal law of gravitation, and then add or subtract them based on the directions that they're going in. So here's what I mean by this. By drawing forces, we want to look at A and we want to look at B. So they're gravitationally attracted to one another. So that means that B is going to pull A to the right and A is going to pull B to the left. Okay, well, A and C are also going to attract, so A is going to pull C to the left, and C is going to pull A to the right, and so on and so forth. So if I think this out and I draw them, this is what's actually going on in this situation, and I'll describe this little notation that I used. So if we look at A, the force of C acting on A, well, it's attractive, so it's going to attract A towards it. C is going to pull A to the right, so is B. B and C will both pull A to the right, which is why those forces act in that direction. For B, since it's in the middle, A is going to want to attract it to the left, C is going to want to attract it to the right, so the force of A on B acts left, and the force of C on B acts to the right. And finally, C is all the way on the right, meaning A and B will both be trying to attract it to the left, so A on C is to the left, and B on C is to the left. I highly recommend you take the time to draw out these forces before you do anything else, because it's going to really help us at the very, very end. All right, now what I'm going to do is I'm going to start to calculate these forces using universal law of gravitation. So I'm going to save myself some time here because I see 6 forces or 6 force arrows on that diagram up top. But because of Newton's third law, I only need to calculate 3 of them because it's an action-reaction situation. So what I mean by that is the force of A acting on B is equal to the force of B acting on A. That's Newton's third law. The only difference will be their direction. So if I set those to equal to one another, I calculate them by using the gravitational constant times the mass of A times the mass of B, and I'm going to divide that by 0.08 squared because that's in centimeters, and 8 centimeters is 0.08 meters. So I solve that out and I get 0.00495 newtons, or maybe 4.95 times 10 to the negative third newtons, depending if your calculator's in scientific notation or not. But I now know the force between A and B. That's not really enough to solve the problem, though. I need to find the force between A and C as well, and eventually B and C. So I do need to calculate A and B, B and C, and A and C. So I'll kind of continue forward with that. So the next thing I will look at is the force between A and C, or C on A, however you want to say that. Gravitational constant again, the mass of A, the mass of C, which is now 200. So if you look above, instead of 950, I'm now using 200. And the total distance between A and C is 18 centimeters, which is 0.18 meters. Square that, plug that into my calculator, I get 0.000206. Well, why is it lower? Well, B had more mass and was closer. When you have more mass closer to you, there will be a larger gravitational force. C has a lower mass, it's further away. Both of those things lead to the gravitational force being less. I'll calculate the force between B and C as well, so I'll use the same gravitational constant. The masses of B and C, which are 950 and 200, and those are only located 10 centimeters or 0.1 meters apart, and I get 0.001267 newtons. Now, those are the forces that they each exert between one another. I don't want to know that as my answer. My answer is what total force is acting on each of these. So now I'm just going to go ahead and I'm going to consider the summation of forces. I'm just going to add or subtract my forces based on those arrows up top. So if I just take a look, I realize that for A, I'm going to say right is positive and left is negative. For A, the force of C on A and the force of B on A are both going to the right. So I'm simply going to add those two together. They're both rightward, they're both positive. So I'm going to add the force of C on A to the force of B on A. For B, the force of C on B is acting right, so I'll make that positive. The force of A on B is acting left, so I'll make that negative, and that's why I'm subtracting the force of A on B when I'm calculating the net force on B. For C, they're both going to the left, so I'm just going to make them both negative. Negative force of A acting on C, and I'm going to add to that a negative force of B acting on C. I could also just subtract it, it's the same thing. But if you look at all 3 of those, Two rightward arrows for A produce two rightward forces. One rightward and one leftward force for B gives me one positive and one negative force. And for C, they're both going to the left, so I get two negative forces. Now I just go ahead and I find the force of C on A, the force of B on A. I just find where those forces are in terms of my calculations. And I can go through one at a time. So for A, the force of C acting on A, which is that pink one in the middle, is 0.000206. And I'm going to add to that the force of B on A, which is in purple, and that's 0.00495. Add those together, 0.005156 newtons. Clearly, by looking at diagram A, that's going to go to the right. I also got a positive answer, which confirms that, in fact, that goes to the right. For B, I'm going to take the force of C on B, which is 0.001267, and I'm going to subtract or add the negative of the force of A on B, which is 0.00495. That gives me a negative 0.003683 newtons, negative implying leftward. So that is 0.003683 newtons acting in the leftward direction. That's simply because the force of A on B is actually larger than the force of C on B, so that's why I get this leftward net force. For C, I'm going to add the negatives of those two values, the force of A on C and the force of B on C. So negative 0.001267 plus a negative 0.000206 gives me negative 0.001473 newtons, negative implying left. So B and C are being pulled to the left. If allowed to move freely, they will begin to accelerate to the left. A will begin accelerating to the right, and you'll notice that if I let that happen, A, B, and C are all going to accelerate towards one another, and that's what gravity does. It attracts objects together.